So I thought I'd go ahead and make a video showing how to do the exit ticket problem from today, 1/4/2022. So you were given the function y equals x plus 4 over x minus 1, and I hope you really key in on what kinds of things you should be thinking about because they apply to every single rational function. So thing number one, what we want to do is we want to be thinking about that every rational function relates to, in one way or another, the parent function y equals 1 over x. So this is the parent. And we've already talked about that where the parent function has two asymptotes. I'll explain how we find those and then why the shape of the graph is what it is. So bottom line, a rational function is made up of a polynomial divided by a polynomial, and all rational functions will be continuous. So all rational functions, all rationals, functions are continuous, meaning that you can draw the graphs without lifting your pen or pencil, except when the denominator is equal to 0. Denominator is equal to 0. Okay, so let's take a look at that. This is a key, kind of a key clue as to what our graph is going to look like. So our denominator is equal to 0. We are in this function can't be reduced anymore. The numerator and denominator can't be reduced. So if x is equal to 0, it causes the denominator to be 0. And in reduced form, whatever x causes the denominator to be 0, that is where we're going to have a vertical asymptote. So x is equal to 0 is our vertical asymptote. And then the other thing about finding where the denominator is equal to 0 is it helps us to understand the domain. So the domain is all real numbers such that the denominator can't be 0. So again, that x equals 0 comes into play. So x can't be 0. That gives us our vertical asymptote. What we also want to look at is how do we find our horizontal asymptote? Well, the Bubble Theorem is how we find our horizontal asymptotes. Bubble Theorem meaning that if the numerator's degree is smaller than the denominator, or the denominator is bigger than the numerator, bigger bubble in the bottom, that means that the horizontal asymptote is y equals 0. It's like this fraction sits there. It can't go anywhere. It can't float up and away because the denominator is so big, it just stays there. So y equals 0 is a horizontal asymptote when the denominator has a bigger degree than the numerator. So we call bigger bubble downstairs. But if the numerator and denominator have the same size bubble, then you just peel off the coefficients. So y equals whatever the coefficients are, the leading coefficients. So that's another clue. Let me fit that in there. Another clue as to how we find our horizontal asymptote. Now, if the denominator has a smaller degree than the numerator, then there is no horizontal asymptote, and we're not going to be dealing with any of those today. But just keep in mind there are no horizontal asymptotes. The other thing is about this function that needs to be understood is that for rational functions will always, the graph will always tend toward the asymptote. So each asymptote, when x gets big in the negative direction, you see the graphs, the y values getting closer and closer to the horizontal asymptote. When x approaches a vertical asymptote, then the graph either goes way down there or it goes way up there, but it's always getting closer and closer to the asymptotes. Same with as x approaches positive infinity, as x gets bigger, the y values get smaller, and in this case, the denominator has a greater degree than the numerator, so the horizontal asymptote is y equals 0. Again, y equals 0 is the horizontal asymptote for this function. We can see we have no intercepts, because if we let x equals 0, that doesn't exist. Can't have a y-intercept, and there's only one way that a fraction can equal 0, and that's if the numerator is 0. So we don't have an x-intercept either. Okay, so let's apply that to our those ideas to our function that you were given for the exit ticket. So how do we find our x-intercepts? We set the we set the numerator equal to 0. So if x plus 4 is equal to 0, then that would imply that x is equal to negative 4. So therefore, we have the ordered pair negative 4, 0. So that would be our x-intercept, negative 4, 0. Okay, so now if you replace x with negative 4, you get 0 divided by negative 5. And 0 divided by negative 5 is 0. Okay, so 0 divided by negative 5 is equal to 0. So when x is negative 4, y is 0. Alright, so then the y-intercept, let's look at that. That's when x is equal to 0. So when x is equal to 0, y is equal to 0 plus 4 over 0 minus 1, which is 4 over negative 1, which is negative 4. So therefore we have the ordered pair 0, negative 4. That would be our y-intercept, 0, negative 4. So we have a y-intercept, we have an x-intercept. Our horizontal asymptote, you may have already noticed this, but the horizontal asymptote, the numerator and denominator have the same degree. The degree is 1. The leading coefficients are 1 over 1. So y equals the coefficients. So therefore, y equals 1 is our horizontal asymptote. So we want to plot our intercepts, and then we want to plot our asymptotes. That's y equals 1. Vertical asymptote, where do we find that? Well, we find that from finding the domain. Well, the domain is x minus 1 is not allowed to be 0. So x is not allowed to be equal to 1. So therefore the domain is all real numbers x, such that x does not equal positive 1. And since we are in reduced form, you can't cancel the factor x minus 1. So therefore x equals 1 is a vertical asymptote. Now, here's the next part. You have to connect the dots. So you connect the dots. We know that negative 4, x equals negative 4 is an x-intercept. We know that y equals negative 4 is a y-intercept. So it goes down like that. Now, we have two other options here, or two options for the right side of this vertical asymptote. Either it starts down here and it moves up to the other asymptote. You have to go from asymptote to asymptote. But if you did that, you'd cross the x-axis. But we only have one x-intercept, so it has to be up here. And that's it.